Hey, it's Masaki from the Dan's Competitive Programming Club, and due to technical difficulties, we weren't able to record today's meeting, but I have some extra information in this meeting that's going to be necessary to solve the final two problems in the practice contest, and also going to be talking about greedy problem solving in general. So the first problem, the sample problem, is going to be planting trees, and you can find it here. John can plant 1 tree per day and needs to plant n different trees that each take a specific number of days to grow. When is the earliest that every tree can be fully grown if John can choose to plant the trees in any order? So we have this planting trees problem. John wants to plant a bunch of trees, but they each grow up at different timings and stuff like that. So you might have a tree that grows in 2 days, 3 days, 4 days, 3 days, and what is the earliest day? You can only plant 1 tree every day. What is the earliest that everything will be grown? And then John actually wants to hold a party on the day after all the last tree has grown up, so +1 at the end. So let's look at the first example. There is 2, 3, 4, 3, and then so a brute force method to solve this problem might be to try every combination of items. So let's say we have 4 different types of trees right here. So we have trees 1 through n, right? And then on the first day, there's n different types of trees that you can plant. And then the next day, there's n-1, n-2, and n-3, all the way up to 1, which this is 1. So this is going to be n factorial. I know I did uppercase and lowercase, but n factorial. And in this problem, n max is equal to 100,000. So this is clearly not going to be fast enough. Generally, for factorial problems, if you are going to try every permutation, maximum is like maybe 15 or something around that range. So 100,000, definitely too slow. So if you think about this logically, John wants every tree to grow on the last possible day. And so you want to plant the tree that grows the slowest on the first day. So you can actually sort this in reverse order from greatest to least, and then plant 4 on the first day, 3 on the second day, 3 on the third day, and 2 on the first day, on the last day. And then afterwards, you wait a bit and see, and then party or something like that. So you can actually simulate this a little bit. So you plant the tree 4, and then on day 2, this tree will be at 3, right? And then you'll plant the 3 tree. And then on the third day, this will have grown to 2, this will grow to 2 days left, and then you plant this tree. And then on the last day, you plant 2, this will take 1 extra day, 1 extra day will take 2 extra days, and then if you simulate it, okay, 0, this tree is grown, this tree is grown, this is at 1, this is at 1, and then 0, 0. So the next day might be here or something. So 1, 2, 3, 4, 5, 6, and then this is the 7th day. And if you look at the sample output, this is 7. So this is it'll take a minimum of the 7th day to party. Okay, and well, if you notice here, you don't need to simulate everything. You only need to keep track of the largest number. So you don't actually need to keep track of all of this. You can keep track of 1 number at a time. So let's do this example 4332 again. 332. You can actually do it in a greedy way where you go 4, and then the next day it's 3, and then this goes to 3. But you only need to keep track of the largest one, so you can keep track of either the largest one from the previous day minus 1, which is 3, or the current day, which is 3. And then in this case, this is equal, so the previous max is equal to 3, and then we have 3. So previous max minus 1 is going to be 2, and then on day 3, this is 3. So you take the largest one, and then it's 3 again. And then on the last day, we have either 2, I guess we'll put on the bottom, 3 minus 1, which is 2, or it's 2, and this is equal. So let's just say it's 2. And then, so this is going to be the number of days, n. It's going to take n days to plant everything, plus this number right here. So yeah, plus this number that we're saving. And then the day after that. So n plus 2 plus 1 in this case. And so code, sample code for planting trees might look something like that. So this is in C++. I'll move it over to the side. Okay. So input n values here, and then for each tree, and then sort it in reverse order. So in C++, you put greater. Different languages, it'd be a little bit different, but sort it from greatest to least. And then current max is equal to trees of 0. So first, on the first day, it's always going to be the maximum number, which is trees of 0. And then every next day, it's going to be the current max minus 1, which is the maximum, the tree that needs the longest to grow on the previous day minus 1, because it's been 1 day, or the current tree that you're going to plant today. And then at the end, you also need to put the plus 1, because you're going to party on the day afterwards. So it's going to be the solution. And so you can see that you need to be able to, for this question, it's obvious if you think about it that you need to plant the tree that takes the longest on the first day, because you need to, and then like n days later, when you've planted all the trees, you get the largest one will have the greatest number of extra days to grow and things like that. So you can therefore prove that the greedy method works for this. So you need to be able to prove that the greedy method works. And so I think with this, you can probably attempt to solve problems B and C, coloring socks and inflation. So if you want to try that and come back, I'll be talking about those two solutions. So yeah. Okay, so for problem B, you have balloons going from, okay, you have n balloons, and they go from size 1 up to size n. So you might have, let's do this example. So you have 6 balloons, 1, 2, 3, 4, 5, 6. This question prompt isn't the best. And then you have 6 gas canisters or something. And you have to pair up 1 canister to each balloon, and you also have to use up all the gas in the gas canister. And then you want to make sure that each balloon is inflated to contains the maximum possible fraction of helium relative to its capacity. So you have 6, 1, 3, 2, 2, 3, and if you sort this will be 1, 2, 2, 3, 3, 6, and it's kind of intuitive to say that 1 fits the capacity for 1 the best, 2 for 2, 2 for that, and then 3, 3, 6, and 3 is better for 2, so you could get this to 100%, right? But if you swap this, this is 75%, and then this is 66% currently, but if you swap it and make this 100%, then this becomes 50%, right? So therefore, you can say that even if you can match it up, it's better to do a greedy method where you can sort it and give the least to the smallest and the largest to the largest, and you'll get the best best maximum fraction of f. So that might be 2/3, such that every balloon can be filled to at least f of its capacity. So in this case, it might be something like that. And this is 60, right? 60%. And I don't think you can make, you can't really make this better than 60% without popping it. And you also can't fill past the capacity. So you can see that a greedy solution works where you sort it and then kind of pair these balloons up with the helium canisters. So this is pretty simple as well. Inflation. Okay. So you input the elements and then sort it here. And then first, double equals 1, answer equals 1, because if you overfill it past 1, then it's going to pop. And so the first thing is going through the canisters, and you're going to use the canister on the balloon with I+1 capacity. And if the canister is greater than that, then because you're using up the canister every time, then you want to output impossible. It's going to pop if you fill it past capacity. So do that, and then otherwise, answer is going to be the minimum of A of I divided by I+1, and if it's greater than or equal to, then if it's greater than, it'll output impossible, so the maximum is 1. So I just had the default values 1, and then minimum here. And there's extra values here. Set precision 8. You don't really need to have it up to 8, but you do need at least 6 decimal places or something like that. So be careful. I tend to do like 1 or 2 more if it says relative error or something like that, just to be safe, and it should be fine. So even if you run the test cases, you might get like 0.60000 or something. It still is within the margin of error, and in this case this is equal, so it's fine. And it should pass within Caddis. Okay, same thing for problem C. If you've tried A and B, you should be able to get this. But C, okay. So you have a bunch of different types of socks, and you throw it into different laundry machines. And instead of doing his laundry in multiple rounds, he wants to buy more laundry machines. And each laundry machine has a specific capacity. They have a color, and the colors that he wants to wash together are going have to have a maximum color difference of K. And so if you look at this example, 530, this is number of socks, this is the capacity, and then this is the difference in color. And then the colors are 0, 0, 1, 1, 2, and K is equal to 0, which means you can only wash socks with the same color. So you can see that in this example, you'd have to wash these 2 socks together, these 2 socks together, this sock by itself, and then it'll take 3 washing machines. So the answer is 3. And with the same numbers, let's say 5, 3, 1, and you can have a maximum difference of 1. So 0, 0, 1, 1, 2. And this time, you can wash the 2 with the same color, and then you can also wash the one with 1 as well. And then you can actually wash these 2 together as well. So you can do this in a greedy way. The examples were shown in sorted order, but I don't think there's I don't think it's guaranteed that you get it in sorted order. So what you might want to do is to sort the socks and then in a greedy way, so you get you can keep track of the upper limit or like of the different sock. And so let's say it's 0, then the upper limit would be 0 plus k. So the first sock, the upper limit, so let's say you throw in one sock into the washing machine, then that washing machine can take up to a color of the first sock that you throw in plus k. And so we can define that as the upper limit. So it would be current sock or first sock. It might be like the first sock to throw in plus k. And so let's see, 0, 0, 1, 1, 2. And so the first sock that we throw in is 0. And then let's say the maximum difference, it's example number 2. So the maximum difference is going to be 1. So this washing machine can now have socks from 0 to 1. Right? And then we go through the array in order because it's sorted, and keep on adding socks if it's within the color and within capacity. So you need to keep track of these two variables, and within the color we can define as like upper limit or something, and within capacity you can save like current capacity or something. So this is the code for that. Oh, I might have hid this with my face in the last one. Color. So again, we're inputting all the colors. You sort it, and then the first sock that you throw in is always going to be the lowest color sock. So the default upper limit, the first upper limit is going to be color of 0 plus k. So the first sock that you throw in plus k. And then current capacity is going to equal 1 because you throw in one sock already, and then answer equals 1 because you need at least one washing machine for the first sock. And then going from 1 to n, although in the question it used like s or something, I'm just used to using n for this type of, for the number of like elements, number of items or something, usually use n, so I just renamed it n. And going from 1 to n, because you already used sock 0, if current capacity is equal to c, then you need to use the next washing machine and define it. Or if the current color is too different from the washing machine, for example, you throw in 0, then you can have color 0 to 1, but you can't throw in a 2 into that washing machine. So in that case, you need to use a new washing machine. So you go increment the number of washing machines, set the capacity to 1 because you're using a new washing machine, and then for that new washing machine, the upper limit on the color is color of I plus k. And then otherwise, you threw it into the washing machine that's going on right now, the one you're filling up right now, and you can increment the capacity and keep on doing that, and then output the answer. Okay. So A, B, and C are a little bit easier, and then D, the question prompt is kind of confusing, but okay. So some viruses replicate by replacing a piece of DNA in a living cell with a piece of DNA in the virus, and so on and so forth. Given the DNA sequence before and after the infection, determine the length of the smallest single consecutive piece of DNA that could have been inserted into the first sequence to turn into the second one. And then a single consecutive piece of DNA might also have been removed from the same position in the sequence as DNA was inserted. So you have DNA, you have string like A and B or something, and then some is removed. So 0 to like question mark elements were removed, and then the virus was inserted. And the virus also is like 0 to question mark in length or something. And so we need to find the virus, the smallest that the virus can be. And the virus can be 0. So let's look at this example. We have A, and then we have A, G, C, G, A. Well, GCG didn't come from anywhere, and they might have removed some part of the DNA, but you can't insert things that weren't there already. So GCG definitely is part of the virus, but this A could have been part of here, and then these double A's, they could have been part of here, and then they might have removed this AA part. So in this case, the answer is 3. So the removal part is kind of the annoying part about this question, in that like it's poorly worded. But basically, with this problem, you have string A and string B, and you want to match the first elements and then the last elements, and keep on removing from the front and the back until and then the what's left in the second string is going to be your answer. So so for virus, I'm using a double-ended Q in order to so you have this before and after strings for the DNA that you're given, and then I'm gonna add it into a deck, a double-ended Q, and then compare the front first. Compare the front values. So A and A are the same, and then A and G are not the same. So this has to be part of the virus. So end, and then on the second half, start from the back. A and A are not. They could be just part of the DNA, the original DNA. So you can cut that out. You can cut that out. But G, again, has to be part of the virus. So the reason why you would use a double-ended Q instead of, let's say, going from... So you could just iterate over the string, right? And then you can iterate up to here, and then you'll be able to keep track up to this specific index or something. Then maybe you check from the back side and go. But there's a chance that it just overlaps, right? Let's say you could say like let's say every single item is equal, right? So looking this in this direction, whoa. Okay. So looking in this direction, you might say up to index 2 is equal or something, and then in this direction, you might say up to index 0 is equal or something like that. So it's easier just to, once you check, to just erase it. And then if you're using a mutable string like in C++, you might be able to like pop back on a string itself, but you can't pop front. There's no pop front in a string. So there's no pop front in a string. So that's why you might want to use double-ended Q, and that makes it a lot easier. And then at the very end, find the size of the second string. So the hardest part about this problem is kind of grasping what you're trying to do with this problem, like what it's actually asking and the removal part. So basically, yeah, that you might remove some of the DNA, but some virus might be there as well or something. So it's kind of not the best problem, I think, but yeah. Okay, and then the final two questions require a little bit more special knowledge. So going back, so these last two problems are going to be greedy scheduling problems, and these are types of questions where you have, let's say you have a job or an event. I guess it's usually like an event scheduling problem or something, and then a job might start at a start time and have an end time. So you have this half open interval of start to end. And then if you cannot fit overlapping jobs into the schedule, or it's often called events, what is the maximum number of events you can complete, or you can events that you can hold or something? And how many can you fit into the schedule? And then what's the fewest number of jobs that can occupy the entire time? That might be a different type of this greedy scheduling problem. So let's say you have a store and you need employees working at every time. Maybe you need to man the store, right? And you want the fewest number of employees working, and they have set schedules, and you can find where they overlap and make sure that at every point in time the store is manned. So this might be a different example of the greedy scheduling problem. So the first one could be reworded as find a set with the maximum number of non-overlapping intervals. So if you cannot fit overlapping jobs into the schedule, what's the maximum number of jobs you can complete, right? And this page has some pretty good graphics, so I'm going to be using that. So let's say you have an event A, B, C, and D, and they have a start time and end time, and then what's the maximum number of events? So you might pick event A and then event D or something. Maybe event A and C. I think for this problem, they're supposed to be overlapping just a little bit. You could select like B and D and fit in 2 events into the day. If you select event C, then C and A are technically supposed to be overlapping, so that would be 1, but there's a maximum of 2 events, right? And C is 3, A is 3, so I guess these are closed intervals instead of half-open intervals. So a lot of the time they're half-open, a lot of the time they're fully closed, so you can't have the end. So let's say an event ends at 3 o'clock, then you can't start the next event at 3 o'clock. So that's the difference between a half-open interval versus a closed interval. And so one idea might be to select the shortest events. So maybe you take A and D, right? And this we'll get to. But this is not always going to work, because you can find a counter to that, where let's say you have 3 events and 2 are very long and 1 is very short. So you greedily select the shortest one, but you can only select 1 in this case, whereas you can see here that you could select the 2 longer intervals, and that would be the maximum solution, so that wouldn't work. Another way that you might try a greedy solution is to select the event that begins as early as possible, but you might have a possible event like a event that starts from the very beginning and ends at the very end. And then with this counter example, you can see that selecting the one that starts at the beginning, that starts earlier than as early as possible, in a greedy way, that's not going to work either. And the actual solution is going to select the next possible event that ends as early as possible. So you want to actually sort by the ending times, and then select the ones that will fit. So A ends the earliest, you select A. B ends the next earliest, but there's an overlap, so you skip. D ends the next earliest, so you select D, and then C overlaps with D, and also A, I guess. But so the solution is to sort by the earliest end time, and if the schedule is open at the current start time, add the current job. And then the other variation is to fill a range with the fewest number of intervals. So the example that I mentioned earlier was, let's say you need to fill in entire working hours for a store. You need to man a store for a given number of hours for a range, and you want the fewest number of employees or something. And each employee can work from like A o'clock until B o'clock or something. You have a specific range. So fill a range with the fewest number of intervals, and you can have overlaps for this one. So in this case, you want to sort by the earliest start time. And so if you go back here, if you go with the earliest start time, then you're always going to be able to fill this range, and then C also fills in the rest of the time. So earliest start time B, in this case, what this pseudocode says is that you would take A, right? Let's say you need to fill this entire range until the end of C. So you take A first because there's no other time, there's no other event that takes place here, so you have to fill it up. Or let's say employees, you need this employee here for sure. And then B, you maybe need it. So tentatively, you'd say you're always going to select this one. So this is the end time, and then the previous end is going to mark where the next employee has to be equal to or before. They have to start equal to or before this endpoint right here. And so B is going to fulfill that. And so so maybe tentatively you schedule in B. You check C. C is still equal to A, so you'd add it in, and then that fills the range. So maybe you just quit at that moment, but let's say you check D. D does not extend beyond C, so you'd skip it, and then that's how the algorithm will go. You can kind of see it right here. So these two things, either sorting by the earliest end time or sorting by the earliest start time, and then you need to think about it a little bit more. It's pretty hard, to be honest, and these both have an extra twist, so maybe take a moment to think about it. So for question grass, problem E, you have N sprinklers and it's L meters long, W meters wide, and each sprinkler is installed at the horizontal center of a strip, and you're given the distance from the left end of the center line, so the X position, and you're given the radius of the sprinkler. And then what's the minimum number of sprinklers to turn on in order to water the entire strip of grass? So this is going to be the fill a range with the fewest number of intervals question. But instead of being given intervals, you're given an X coordinate and then a radius. So you're going to have to do some trigonometry, everyone's favorite, right? So let's say you have a circle. I don't know how to... Okay, let's say you have a circle, and then you have lines, and this is going to be equal, and then this is going to be equal to the width, right? And you have here, this is the x, and then here you have this is going to be equal to the radius. So the circle range that fills this entire strip of grass is going to be right here. So what is this right here? And then here, if you can find here, this area right here, that's the amount of area that you can fill with every sprinkler. So if you think about trigonometry, you can say this is equal to r as well, and then this right here is equal to w over 2. This range right here, from here to here. And then you want to find the distance here. And then this is a right triangle with hypotenuse r. So you might notice that this is right triangle, so you can use Pythagorean theorem. And so a squared plus b squared is equal to hypotenuse squared. So let's say like r squared or something. And then r squared, and then 1 is w over 2 squared. So let's just call this w over 2 squared. And then how do you find this distance here, which is a? So a is going to equal the square root of r squared minus w over 2 squared. And so you can find the interval is going to be, x minus this a, and then x plus a. So you have this interval from x minus a to x plus a. Okay. And so, yeah, it's kind of annoying, but once you get the interval, now you can solve it, fill a range with the fewest number of intervals. So now we need to, the next thing we need to do is sort by start, and then fill in the ranges. And to be more specific, this is x minus a, but we don't care if it's negative. So you can say the maximum of x minus a comma 0. Maximum of x minus a 0. And we don't care if it goes out of bounds. So x plus a, the minimum of L, I guess I'll make it positive L, uppercase L, or x plus a. So in order to, I'm just going to trim it down to 0 and trim this down to L. And so we are now able to convert it into this problem. And what you want to do is, well, first you might want to identify things that just aren't necessary. So let's say you have this circle here. The circle, if the radius, let's say you have the strip of grass, and then if this radius is less than this length, which is w over 2, if r is less than w over 2, then this sprinkler is kind of useless. You're going to need a sprinkler that does its job for it, so you can skip that. And then you can also skip if so you have this circle here, this sprinkler, you have this sprinkler right here, you have this sprinkler right here, and if you use both of those, then this becomes useless. So you need to start looking at that, and then this overlaps just a little bit, but it's necessary to use up this little triangle, and yeah, so it's really annoying, and I honestly had to like look up a solution for this and learn about it a little bit. Yeah, really annoying. But the first step is to find the distance. So I went ahead and for every test case, I did for every test case, I went ahead and pre-computed w over 2 and then w over 2 squared, because you're using it every time. You don't really need it. I don't think it's the time, you're not too stressed on time, but you're always going to do radius times radius minus half of w squared. So I just went ahead and computed that. You don't really need to do it n times, right? So went ahead and did that, and then if radius is less than half w, continue, and then distance is equal to square root of radius times radius minus half w squared. So you got the Pythagorean theorem, you got this triangle here, so a squared plus w over 2 squared is equal to r squared, and then if you move it around, you can find that the distance, a here, is going to equal square root of r squared minus w over 2 squared. And then, so the sprinkler, you find the intervals, the beginning and end intervals for the sprinkler. And then this is just like a pair structure, and I want to sort the sprinklers by beginning time. So I made sure to sort by beginning time, and if the beginning times are equal, then I want the one with the end time that goes later. So if two sprinklers have the same beginning time and have a different end time, then that means the larger one is like strictly better sprinkler. So I want the better sprinkler first. So that's why I put this here. That's why that's there. And then sort it with the custom comparator. And there, this is a vector sprinklers. And then if the next sprinkler doesn't go past the furthest point for the next for the previous sprinkler, so let's say you sort it by start times, right? So you take this sprinkler, and then you take this sprinkler, and then the next sprinkler start time is this. So if this sprinkler, the end time is this end time is before this sprinkler, so this will never be better, right? So you can eliminate that. Basically is what it's doing, but this sprinkler goes past it, so this could be a potentially good one. Maybe there's like another sprinkler here that gets this area here, but it goes further. In that case, you might want to get rid of this sprinkler, but at the moment it's the next best candidate. So that's why you might want to do a line like that. And then at the very end, we have the thing I wrote in pseudocode in the presentation. So target is just going to be the previous end. Maybe I'll rename it. So previous end, and then next is going to be next end, and then so let's say you're doing this. Previous end is equal to 0, next end is equal to 0. So we want a sprinkler that has a beginning time that's equal to or less than this 0, right? To fill this entire strip, it has to be 0. this interval has to start at 0. So the initial point is 0, and then the initial number of sprinklers is 1. And then so you select this sprinkler, it goes up to here. If there was another bigger sprinkler like also at 0, then maybe you pick that one, right? And then if previous end is equal to next end, okay, is equal to false. So when would previous end be equal to next end? That's when some area isn't covered. So yeah, if you look at it, that's how the logic works. But yeah, honestly, kind of hard. It's probably easier interval questions, especially because this uses double. So yeah, not the best question. Okay, final question is classrooms. And then classrooms is like, there's an extra step that's harder, but it's also a little bit easier because it uses whole numbers, and the logic for finding the maximum number of non-overlapping intervals is a little bit easier as well. So okay, so you have numbers n and k, the number of activities and the number of classrooms, and then you're given n lines for the start and end of activity. So you have like 1 to 4, you have 2 to 9, so 1, 2, so let's say you have a time range 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, 9. And then we have 1 to 4, 1 to 4, we have 2 to 9, 2 to 9, and then we have 4 to 7, 4 to 7, 5 to 8, 5 to 8. Okay, and then you want to fit in the maximum number of proposed activities. So 4 to 7, even if two proposed activities overlap momentarily, they cannot be assigned to the same classroom. The ending time of one activity equals the starting time of another activity. So here, this ends at 4, this starts at 4, you wouldn't be able to have it in the same classroom. So for this type of question, you have to sort by the earliest end time. So the earliest end time, second earliest end time, next, right? And so you might want to fill up the first classroom is full until time 0. Second classroom is full until time 0. You select 4. This is the earliest end time. So replace 1 with 4. And then the next one ends at 7 and starts at 4. 4 cannot be, you can't go to this one. So cross this out. So the start time has to be greater, and then it ends at 7. And then you have 2 total classrooms. The next one starts at 5, ends at 8. 5 can start in this one, so and ends at 8. So 8. Then we have something that starts at 2, and 2 can't fit here or here, so you have to skip the last one. And then total number of activities is 3. There's no extra one, but so the basic thing is, the first thing to do is to think about like one classroom. So 1 to 4, and then 4 to 7 you can't, you'd have to skip, and then 5 to 8 you could add in, right? So you have 1 to 4 and then 5 to 8, and so you would save 0, and then you would save 4, and then you'd save 8, right? So you can do one classroom with one integer, and you can save the end time. The current, like like next available or something. Next available at, you know, like at something o'clock, right? So you need to save this interval. And then let's say you have a bunch of classrooms. So you have classroom like, let's say you have like 5 classrooms, then you might have 0, 0, 0, 0, 0. And then your next activity ends at 4. Then, and starts at like 1. So all these can fit 1. So maybe you take this and then go 4. And then if you could sort this 0, 0, 0, 0, 4, and then next activity starts at 4 and goes to 7 or something. Well, 4, I want to pick the largest value where it's less than 4, right? Strictly less than 4, and it can't be 4. So it's going to be this. So you could actually do lower bound, and then go like minus minus, like go back. Lower bound minus 1. So find the lower bound, which if you looked at the binary search presentation, this is the, in a range of values, the lower bound would be the number where the index, like array of index is less than or is greater than or equal to, the lower bound is defined as the point where the array of that lower bound, so the array of lower bound is greater than or equal to that target value. So for 4, the lower bound would be 4, and then so take a look at the binary search presentation if you're not sure about lower bound. And the new thing about lower bound for this problem is that you can actually run lower bound on sets and maps if they're tree sets and tree maps. You can actually you can run lower bound on tree sets and tree maps, and those are sorted lists. So you can update this list of classrooms and update the time, and then say you change the next one to 6, then you can remove from a tree and then insert back into the tree, and so remove in order of log n and then add in log n time. But the issue with a set or like a binary search tree with set is that this only has unique values, right? So you could either use a multi-set, or you could have a map and a tree map where you do int where the key value is equal to the end time, and then the value will be like number of classrooms with the end time. So you can store it in a tree map as well. And then you can actually binary search on the key values in a tree map. And then the rest is just like the regular scheduling problem. So yeah, this is kind of a hard problem, but so I have structure activity. So I just wanted to be able to sort the activity by the end times, right? I want the earliest end time going first, and this doesn't really matter actually, but yeah, the most important part is sorting by end time. And yeah, you can also do the same thing by having a pair of int or something, and having a custom comparator. It doesn't matter. I just defined a custom class for this. And so you have int and k, input in, read in all the activities, sort it by the end times. And then now I have a tree map, and m of 0 is equal to k. So first you have k classrooms with 0. So that's why m of 0 is equal to k. And then first you start out with 0 classrooms that can be used. And then if you can find the lower bound, so let's say all the classrooms are full until like 4 o'clock, and then you do 4. The lower bound for that, you're going to get the first value. And so if you get the first value, that means that there are no values in the array that are strictly less than your value. So continue. You can't do that event in any classroom. And otherwise, go to the one before it and then use that classroom. And then I insert into the map the new end time and decrement the start time for the classrooms. So let's say it's zeros, then I want to decrement for the zeros, but let's say there's no more zeros, then I don't want to go to -1, I want to erase it instead. So that's the logic there. And if you're able to use that classroom, that means that you were able to have that event work. So you can increment the answer, and that's going to be it. So the secondary part is definitely pretty tricky. We probably should have, I actually wasn't aware of the greedy scheduling problem until like today, like literally today. So yeah, we probably should have planned it a little bit better and had a easier greedy scheduling problem. Classrooms and grass, they're both kind of tricky. They both have like pretty big pitfalls where this uses floating point numbers and trigonometry, and then classrooms has the thing with the having to binary search at the end and have a sorted list, having the tree map, and that's kind of tricky. So we really should have had a more basic problem. But yeah, hopefully that was helpful. So, thanks for watching.